Should I use that? Okay, so this is a little animation of two neutron stars orbiting each other and in spiraling to finally merge, and they release gravitational waves while doing so. In 2017, we detected gravitational waves for the first time from such an event. It was this GW170817. And since then, in the 3 observing runs that the detectors have had till now, we only detected one other such event, GW190425. But the 4th run is still ongoing, so we may be able to see a few more such events. In the near future, we will have advanced telescopes like the Cosmic Explorer CE and Einstein Telescope ET coming up, which will increase our sensitivity range by a huge amount to up to a redshift of 10 to 100. This green line here is the range of Einstein Telescope, and the pink line is the range of Cosmic Explorer. And these yellow dots over here are the neutron star mergers that we will be able to detect. So you can see we are going to have our hands full with a huge amount of data coming in. This large population of binary neutron star systems will have all kinds of events. So we need to be prepared to study these. In this research, we are studying one such system which has very high magnetic fields. Now, why is it important to study the effects of magnetic field on BNS systems? Magnetic fields can induce corrections to tidal deformation. The magnetic field of one neutron star can tidally deform its companion. And if the magnetic field of the stars is greater than 10 to 16 Gauss, then the contribution, the correction to the tidal deformation that is introduced can have a sizable contribution, and it may even be able to, we may even be able to see it in the current detectors. The magnetic fields can also influence the dynamics of the inspiral and thereby delay or accelerate the merger, and thus it can change the observed signal of the gravitational wave event. So to accurately model BNS systems, we need to study this effect to make sure if it is having a significant impact on the waveform of the binary neutron star merger. The systems that we are considering have magnetic fields between 10 raised to 16 and 10 raised to 18 Gauss. This is theoretically permissible because the theoretical limit to magnetic fields of neutron stars is 10 raised to 18 Gauss, so anything below that is allowed. And in typical binary neutron star systems, what happens is even if the neutron stars start out with high magnetic fields, by the time they come close enough for the fields to interact, the magnetic fields have decayed to lower strengths. But the systems we consider will have high enough magnetic fields at the time of interaction. For this to happen, we need to look at high density environments such as globular clusters. Globular clusters are tightly bound clusters of stars and can have tens of thousands to even millions of stars. Such a binary can be formed in globular clusters through dynamical capture, where one neutron star gets gravitationally bound with the other neutron star. And a binary formed like this will have high magnetic fields and as well as high eccentricity because it was formed through dynamical capture. And this is the system that we're looking at. We did a small analysis with the ATNF pulsar catalog. This stands for Australia Telescope National Facility. It is a catalog of all the pulsars that have been detected till date. So we plot the age of the pulsars on the y-axis and the magnetic field on the x-axis. And the pulsars seem to follow this linear trend. If you extrapolate this linear fit and look at this area, 10 raised to 16 to 10 raised to 18 Gauss, you can see that if any pulsars have this magnetic field and if they follow this trend, the age, they will lie somewhere around here. So the age is positive. That means our systems have not been excluded by the observational analysis too. So theoretically as well as observationally, it's fine, we are good to go. We use two metrics to study this effect. One is the rate of energy loss due to gravitational radiation and how the magnetic field is changing it. The next is the number of cycles. What does this mean? So you can see this plot here. This is actually the gravitational waveform of the first ever event that we detected in 2015. This is a binary black hole merger, but the waveform of a binary neutron star event is similar. So if you look at the bottom plot, this one maxima and one minima, you can consider it to be one cycle. Because of the interaction of the magnetic fields, it may happen that there are additional cycles, there are some cycles added to the waveform or some cycles subtracted to the waveform. So we are going to see if this may happen. First, we look at magnetic fields in the case of circular orbits. And one of the quantities we look at is the rate of energy loss due to gravitational radiation. It has two components. The energy loss caused by pure gravitational waves, that is in the absence of any magnetic interactions, and this magnetic field corrections. So the magnetic dipoles of the two neutron stars interact, and that is where this magnetic field correction comes in. We also look at the rate of energy loss due to electromagnetic radiation just to compare the two. And if you plot these quantities, you get something like this. This topmost red-blue curve is the total total energy loss due to gravitational radiation. This green curve is the magnetic correction to the gravitational radiation, and the orange curve is the energy loss due to electromagnetic radiation. These attractive and repulsive are two orientations of the magnetic dipoles. The magnetic dipoles can have any orientation between the two. I just use these two for representation purposes. If you compare the two plots, in the magnetic correction in the repulsive case and the attractive case is almost the same, but it's a tiny bit higher in the repulsive case. Whereas the energy loss caused by electromagnetic radiation is higher in the attractive orientation compared to the repulsive orientation. Next, we look at the effect of tidal deformation in eccentric orbits. Here we don't look at magnetic fields. We assume magnetic fields do not interact and just look at these two quantities. So there are a bunch of things here. The topmost curve, the blue curve, is the total energy loss due to gravitational waves for a system in eccentric orbit. This light green curve that you see is the contribution from terms involving only eccentricity. This orange curve is the contribution from terms of involving only tidal deformation, and this dark green curve are the coupling terms, the coupling between tidal deformation and eccentricity. And you can see that the contribution from eccentricity is a lot more significant than that from tidal deformation. So this is one thing. Next, we look at the number of cycles. We study this in the case of magnetic fields in circular orbits. And we observe that for 10⁻⁵ Gauss and higher, as you increase the magnetic field by 1 order of magnitude, the number of cycles improves by 2 orders of magnitude. What does that mean? So for example, if my magnetic field is 10⁻18 Gauss, then the effects of magnetic field cause a change of more than 1 cycle per 10⁻³ cycles. So for 10⁻17 Gauss, that will be 1 cycle for 10⁻⁵ cycles. This change, more than 1 cycle for every 10⁻³ cycles, is important because this can also be detected. So if we are able to detect the gravitational waves from such a system, then this effect may be observed even by our current detectors. So it will be even more significant with the advanced detectors like Cosmic Explorer and Einstein telescope. Next, our plan is it is currently ongoing. We want to incorporate the effect of magnetic fields in eccentric orbits. And then finally, we will look at all three of these effects together: magnetic fields in eccentric orbits and also tidal deformation. So yeah, thank you.
Questions? Maybe I can ask questions as well. Yeah, if you could go back to the waveforms, did you say something like if there is a magnetic field component, there will be more cycles?
more or less, depending on
So-
what the effect is.
So just by seeing the waveform, you can deduce the magnetic field. Are you saying something like that? Just by seeing the waveform of some neutron star merger, can you deduce the magnetic fields? For instance, the two events that you talked about.
It may be possible because the final goal of this analysis is to eventually look at the waveform. So, do you know how parameter estimation is done?
Roughly.
Yeah, so if so you will have waveforms with this magnetic field and these many cycles, and then you can compare it to the data and see if you are getting something similar. Then you will be able to tell if whatever the strength would be.
So just to follow, in the two events that we have detected, do you have an idea of what the magnetic fields were doing?
No. That is the goal. Once we get the waveform, we'll look at past data and see if we are able to see anything.
Okay.
Yeah.
How far are you from building a phasing model?
What? How far?
The phasing correction. How far are you from building a waveform model, including
a long
magnetic
distance.
fields? Yes.
Yeah.
Long way.
Yeah.
How long?
I'll tell you later.
Okay.
Few months.
Yeah, maybe.
Yeah. Could you say a bit more about what magnetic effects are you taking into account in these statements?
Dipole-dipole interactions of the two. I have the equations. Yeah.
Okay.
So these are the magnetic corrections that come in if you assume only dipole-dipole interactions between the two magnetic fields.
Okay. So these are these come from what is the okay? Let me see. What are the physics of these things? That there's a tidal deformation.
No.
Is it-
In this case, you are not considering tidal deformation. Only the magnetic field is present. So you just take the dipole-dipole interaction and add it to the Lagrangian, and then evolve the equations and get this E dot finally.
Okay. So you're working with point-like approximation. You're still treating neutron stars as points.
Yes.
And in the inspiral, you're asking the presence of dipole magnetic fields. How does it affect the gravitational wave loss?
So the magnetic field analysis is separate from the tidal deformation eccentricity analysis. We haven't combined the two yet. So for this, we are considering them to be
So this is just okay. And maybe I can make out, but maybe you can just tell me like at what. So this is some post-Newtonian analysis, right?
Yes.
So at what PN order is it? Is it
2.5.
2.5. Okay.
Very small question. So if you can go to the beginning slides where you were showing the horizon distance of the CE and the other thing, Einstein telescope. Yeah. So I noticed that for the BH mergers, Einstein telescope seems to be better than Cosmic Explorer, whereas that's not true for the neutron star mergers.
Yeah.
Any particular reason why that's the case?
I don't know about it. Why is the sensitivity different for neutron stars compared to black holes? So,
No. Why is ET better for black holes, but CE better for neutron stars? Okay, thanks.
Can I answer this question? Can people hear me?
oh, yeah.
Hello. Oh, so I think the reason behind is this. So ET is sensitive to low frequencies more than the Cosmic Explorer. And since heavier masses will merge at low frequencies, so it can go to higher distances for black holes. But while on the other hand, the BNSs will merge at higher frequencies where CE is more sensitive. So I guess that is the reason.
Next question. Yeah, so I just want to understand the effect of magnetic field is more visible in the gravitational waveform if it is greater than 10 power 15 Gauss. Is that the statement?
Yeah, 10 power 16 Gauss.
10 power 16 Gauss. Okay, just below that, there is no significant modification to observe it in any of these future bands.
Yes.
Is that strictly
Even
correct?
10 raised to 16 Gauss is very small, but
Right.
still we have to make do with it.
Yeah, just to understand one more thing. Instead of a binary neutron star, if we take just a single neutron star which emits continuous gravitational waves, do we know anything about what is the effect in that case, like the effect of magnetic field on the continuous waveform?
That will be different because here we are not considering self-magnetic field interactions. Here we are looking at how the magnetic field of one is affecting the other. So I don't know how it will be if there's only one neutron star. If Aditya is there, is Aditya there online?
So I'll answer this one. So for a single neutron star, the magnetic field deforms it, and the continuous gravitational wave that is produced, that depends upon the ellipticity. The more the magnetic field, the more will be the deformation, and more will be the gravitational wave emission for a continuous gravitational wave.
What's the strength of the magnetic field when this will be evident?
So it depends. Like as of now, we have not observed any continuous gravitational wave detected yet in the LIGO detector.
Yeah, okay.
So we have some estimate of what will be the ellipticity and what can be the magnetic fields for those systems. Some constraints on that.
Okay. Thank you.
Thank you. So that's all for this session.